So large projects, so we're going to talk about project planning. So large projects are usually broken down into many smaller activities or tasks that need to be completed one at a time. And sometimes the next activity can't begin until the activity beforehand has been completed. So when we're talking about project planning, we could be talking about building a house or making a cake, any sort of activity that can be broken down into any sort of subtasks. So if we're talking about making a cake, for example, my steps might, I got to, put all the ingredients in, I've got to mix it, I've got to pour it into the pan, I've got to put it in the oven to bake. But there's this idea here that some activities can't begin until the next activity before the activity before has been completed. So I can't mix my cake until I've cracked the eggs. I can't put my cake in the oven until I've poured it into the pan. So there's the idea that some activities require certain other activities to be completed first in order for us to be able to successfully complete the project. And this is where we can run into scheduling problems and we could waste a lot of time and money. Because if, for example, we were building a house and we had the people rock up to put the frame up, we said, oh, sorry, the concrete guys aren't coming for 5 hours. Then the people that have come to put the frame up are just going to have to sit around and waste their time because we weren't organized enough to make sure that the concrete was done first. So that's the idea of a scheduling problem. Because we want to find the most efficient way to do our projects. And that's what critical path analysis is all about. It seeks to find out what activity needs to be completed by when so that we can do everything in the least amount of time to maximize efficiency. So this is an example of a path here. Sorry, not a path, a project here. So we see writing header file A, writing header file B. These are all the different activities that need to be done. So this project is about designing some sort of software, and these are all the little individual sub-activities they've broken it down into. You can see that in this activity table, it also lists the time taken for each activity, and this column here is about the immediate predecessors. So this is about what activity must be completed before each activity so that the next activity can begin. So here we can see that activities A and B, so writing the header file A and B, don't have any immediate predecessors. That means they can be completed right at the start of the activity. And then when you look down to activities C and D, coding implementation for A and coding implementation for B, you can see that they do have immediate predecessors. They have activities that must be completed before these activities can begin, because you can't do the coding implementation before you write the header files. I don't know what that means, but I can tell that this has to happen before this, because I've been told that A is an immediate predecessor for C and B is an immediate predecessor for D. So they have to happen before the next activities can start. You can see again how we're going to run into scheduling problems if we don't make sure that that runs smoothly. And this is actually a graph or a network that represents this. So I want you to maybe spend some time having a look at this because it's quite interesting really. Because you can see that A and B can start at the beginning because they don't have any immediate predecessors. But you'll notice that both C and E have A as an immediate predecessor. So once A is finished, then C and E can start. You can also notice that G, for example, needs C and E to be finished before we can start task G. So let's have a look at G. We can see that G, this shows here that C has to be done before G can be done, but this little dotted line here is also indicating that E has to be connected, so that E has to be done before we can start G. This is what we call a dummy line. So it's a dotted imaginary activity task or line with a weight of 0 that's purely like a notational convenience. Dummy lines just exist to communicate like immediate precedence, for example. So because C is an edge and E is an edge, because edges represent activities when we're looking at this, I can't have G come out of C and E. That just doesn't make sense. I can't have it come out of two different vertices. So that's where dummy lines come in. By linking up there, we can see that, okay, so before I can start G, I know that C and E has to be done. And you can also see that this network is directed, and that communicates that like the tasks have to be done in a certain order. And we can see that flow throughout the network. And like I said, activities, they can be represented visually in networks, like what we have here. Oh, and I've already covered this as well. So the start of an activity depends on any predecessor activities being completed first. So immediate predecessors are activities that, once completed, guarantee that the current activity can be started. So think of immediate predecessors like prerequisites. You have to do year 10 before you can do 11. You have to do grade 3 before you can do grade 4. You have to crack the eggs before you can stir them in. Think of it like that. So edges are what represent the activity to be completed, and the weights represent the duration of the activity. So it might take 3 days for them to lay the concrete, for example. And then the vertices represent the start and the ends of the activities on either sides of the edges. And the dashed lines, which are the dummy lines that have a weight of 0, what I introduced earlier, they're required when 2 activities share some but not all immediate predecessors. And that accounts for shared immediate predecessors without needing multiple edges. So they're imaginary lines. They're a notational convenience to communicate that need. It's to communicate that this activity needs both of these as immediate predecessors without needing multiple edges. So we've covered that there. So the earliest start time an activity can commence is important because we want activities, most of the time we want to start activities as soon as possible. And not all activities can be started at the beginning due to predecessors, like what we've already talked about. And the earliest start time is found by forward scanning. So A and B, because they don't have any immediate predecessors, they can be started right at the beginning of the project. They can be started at time point 0. But we know that C and E can't be started until A has started, till A has finished. So if this, for example, represents hours, then C can't start until A has finished. So C can't start until 2 hours into the project. So the earliest time that C can start is whenever A can finish. So C can't start until we're 2 hours in. And we know that E is the same. E can't start till we finish A, so we can't start E until we're 2 hours into our project. Let's have a look at G. We can't start G until C and E are finished. So it'll take us 2 hours to finish A at the absolute quickest, and then it'll take us 10 hours to finish C. And then if we look at E, it'll take us 2 hours to finish A, 5 hours to finish E, and then we can come up here along the dummy line. So to get to this time point to start G, we can have A done in 2 hours, which means we can have A done by the time we're 2 hours into our project. We can have E done after 5 more hours, so we can have A and E done after 7 hours. So E is ready to go after 7 hours, but at 2 and then another 10 hours means A and C won't be done for 12 hours. So we actually can't start G for 12 hours because both C and E need to be finished for G to start. So that's kind of a theoretical introduction to how we use forward scanning to find the earliest start time. So for the sake of time, we're not going to go into this. I'll just continue to give you a bit of an overview of some of our most important information. But the basic idea of forward scanning is that we move through the vertex and we find the earliest start time of each activity using the process that I just modeled on the previous slide. And the earliest start time of each activity, we record that in the box on the left at the vertex at the start of the activity. So you can see that what I said here is true. A has an earliest start time of 0. It can start straight away because it has no immediate predecessors. C has an earliest start time of 2 because A takes 2 hours. So by moving along there, we can say that A has an earliest start time of 2. Then we can come down to E. E is going to take 5 hours. So this number here is going to be 7 because we know that it's going to take 7 hours at the absolute quickest and earliest to get to this point. But then if we come across up here, well, technically we could be here by 7 hours, but because it's going to take us 12 hours to get A and then C done, then we know that the earliest time we can start, G, is actually going to be after 12 hours into the project. So when we do forward scanning, we always choose the biggest number because we're always going to be held up by the task that takes the longest. And we are almost out of time for today, so I definitely encourage you to download the slides and go through each of them. I've put quite detailed instructions on each of them, so hopefully they'll make sense along the way, and I'm not going to have time to explain most of them, unfortunately. But we have gone through the earliest start time, and then latest finishing time is kind of the reverse, and we do that via backwards scanning. So the latest finishing time is what is the latest time I could finish this activity without holding up the project. And then we do that through backwards scanning, which you can see we've done in this graph here. And then by doing that, that can actually help us find out the critical path. And the critical path of an activity is what is the order or sequence of activities that, if delayed, will delay the entire project. What can we not hold up if we don't want to delay the whole project? And if you follow the path of numbers of boxes where the numbers are the same, that will actually help us find the critical path, which we can see in this here is along the top. So we can see that these activities are on the critical path. So if any of these activities are delayed, then we know it's going to delay the final finish time of the project. So that's just a really brief overview